Hello, good morning. Calculus 2, Chapter 7.2. We started doing volume of a solid of revolution. That's what it's called, the volume of a solid of revolution. Can't be any solid, I guess. You have to take a two-dimensional region, spin it around an axis, and that makes it a solid of revolution. And we use the disk method for now. We'll learn another method coming up in section 7.3. But in 7.2 we use what's called the disk method. I didn't even write that down, the disk method. And there's these formulas. Look, it's a lot of formulas, I know. But if you're going around a horizontal axis, if your region is going around a horizontal axis, which I did in the last video, then this is your formula. You're working in x's. The thickness of your disk is dx, so you're working in x's, and you have this formula, or if there's a hole in it, you have to subtract out the inner volume that you don't want. So if your region, if your solid generated by revolving the region ends up with a hole in it, there's a gap of empty space you don't want, you have to subtract out that inner volume. So it's an outer volume minus an inner volume, which is this formula. Now your book calls that the washer method. It means your disk has a hole in it. It's like a washer. That's okay. You can call it the washer method. I kind of prefer not to. It makes me think it's a completely different method, and it's not completely different. It's the disk method with a hole in it. So anyway, so you got to find the outer radius and the inner radius and subtract that. You square them and subtract them to subtract out the inner volume. So around a horizontal axis, you're working in x's. The thickness of your disk is in x's. Hey, if you spin something around a vertical axis, then you're working in y's. And you could have a hole in it, so you could have the washer method, or you could subtract out the inner radius. So an outer radius, function of y's, the bounds are in y's, dy, it means the picture is like this. Your disk is running sideways. The thickness of your disk is dy as opposed to dx. So that's a lot of formulas. It's, I'd like you to know them. I'd like you to memorize them, but you can memorize formulas or you can understand the concept. It is pretty easy. It's pi r squared times the thickness of the disk. And you're adding up a bunch of circles with a little thickness. They're not circles, they're disks. So it's cool to understand it. And in this one, you're subtracting out the inner volume. But that's a lot of formulas. Let's look at a problem or two. So I looked at this problem last time. Y equals the square root of x, y equals 0, x equals 4. That's the boundaries of our region. There's a picture of our region. And then to define the problem, and somebody has to say, find the volume of the solid generated by spinning it around an axis. So if I said spin this around the x-axis, maybe you can imagine that, and that's the problem we did last time. And that was an easy problem. That's nice when it sits on the x-axis, spins around the x-axis. That's a typical, that's this formula, and we did that last time. Okay, so this time I want to change the problem. So here's the problem. Same region, but it's a different problem when I say spin it around the y-axis. Different problem. So, and my little notation is this. I put a little symbol there that says I'm spinning it around the y-axis. And then I'd like you to imagine that. And then my first question to you is there a hole in it? Because that helps me figure out what formula I'm using. Also, because I'm going around a vertical axis, I guess all of a sudden I realize, oh, I'm going around a vertical axis. My disc look like this. The thickness of my disc is dy. I'm going to be working in y's. My formulas will be in y's, which means I want my functions in y's, which means I want my functions solved for x in terms of y. Let's just do that. The name of this curve was y equals the square root of x, but if I solve for x in terms of y, I would square both sides and x would equal y squared. So there's the name of my picture in terms of y. This is the name of it in terms of x, the name of the curve. Okay, all right, I think I'm working in y's, and here's my question, is there a hole in it? And I've argued with students about this before. I don't want to argue with you. The answer is yes. If you drew a representative disk, would it have a hole in it? Would there be would it be a washer? Would there be a hole in it? Would there be a gap of empty volume that you don't want? And the answer is yes. Even though this shape would touch right there. So by the way, here's the shape. If I drew the shape, this is me trying to draw the three-dimensional shape. It would look like this. And if you drew a disk, here comes a disk of volume. There's a hole in it. There's a chunk of volume I don't want. So you got to imagine this spinning around the y-axis. It's like a hockey puck with a funny little divot taken out of it. And even though the hole might not go all the way through because it does touch right there at the bottom, any disk you draw will have a hole of empty volume you don't want. So there's a hole in that. I think you're convinced. So I'm working in y's. There's a hole in it. All right, there's my formula. I need two things. I need my outer radius and my inner radius, and then I'm good. By the way, in this picture, when x is 4, you can plug it into this function, y equals the square root of x. And when x is 4, y is 2. So there's the y value there. And I'm going to have a disk. And I need an outer radius. I call that big capital R of y. It's the outer radius. And it is that x value, which is 4. It doesn't vary. It's not a function of y. It's a solid 4. And then I have the inner radius, which is this goes to where the hole is, okay, because there's a disk here, the hole in it. And the inner radius does vary. That hits the function, and that distance x is the function, which is y squared. So that inner radius is y squared. And I don't subtract the two functions, I square them and subtract them. I find the volume of the outer, which is pi r squared times the thickness, and then I find the volume of the inner, which is pi r squared times and I subtract them. So it's this formula, square them and then subtract them. So here I go. This is pretty easy. It's a 4 squared minus a y squared dy. My outer radius minus my inner radius. There's a pi out front, and my bounds. Sometimes the bounds are the tricky part. Some students get confused, but those disks are going to move from throughout that space from 0 to 2. I'm working in y's. The bounds are y values. They're not the x values. So 0 to 2. That's cool. I mean, you're working in y's, there was a hole in it, you had to, that's kind of a more advanced problem than the one we did last time. You square it, you integrate, you evaluate, and you get an answer. I think you can do that. I could do that for you or with you here, but I think you can do it. I'll do it real fast if you don't mind. When I square it, it's a 16, and when I square that, it's y to the 4th. When I integrate, I get 16y minus 1/5 y to the 5th. And I'm going to evaluate from 0 to 2. Is there anything I've forgotten there in my sloppiness? Oh, pi. There's a pi out in front of that. Don't forget the pi. And now you plug in your 2 and you evaluate. You get 32 minus 32/5 times pi. Everybody knows that's 128/5 pi. 128/5 pi. Sometimes I rely on you to double check me. I could go, anyway, I'm not always right. I could make mistakes. I just added those fractions quickly in my head. I think I'm right. I want to do another problem while I got you here. Let's do another problem. So I'm going to erase this. Let's see, I'll erase this one. I don't need all these formulas necessarily. Hopefully you got them memorized. They're in the book. I wanted to refer to them, but I got them memorized and I understand the process. It's pi r squared. Okay, so this comes from the book. This is a problem out of 7-2. It's number 18. And number 18 says I've got y equals 1/2 x cubed as one of my functions. X equals 0 and y equals 4. Now those are the boundaries. The way the problem is worded is it says, find the volume of the solid generated by revolving the region bounded by, so the region is bounded by these boundaries, and that creates a two-dimensional region. We spin it around something to create a 3D solid, and we find the volume of that solid with our awesome formulas. This problem wants me to spin around, you know, that last problem was spin around the y-axis, and I've done one earlier, spin around the x-axis. We're talking about a vertical or a horizontal axis. You know, so it doesn't always have to be the x-axis or the y-axis. So this one says spin it around the line y equals 4. Around the line y equals 4. So we need a good picture of this. So let's see what we got. Let's see what we got. We got this 1/2 x cubed. Okay, well that's just a cubic function that's been a little bit stretched or compressed. There it is. Good old cubic function. X equals 0 is this vertical line here. X equals 0. Y equals this. That's 1/2 x cubed. And then y equals 4 is a horizontal line. Y equals 4. So this is the region. You know, sometimes you shade the wrong region or sketch the wrong region. Be careful of that. The region is well defined. It should be well defined. Now they want me to spin it around y equals 4. Okay. That's pretty cool. I can imagine that. You got to imagine it maybe. I don't really have to draw the 3D thing, although I could try. You know. Huh. I don't know. Something like that. Some kind of interesting shape with this cubic function as your guide. So I'm going to point to this. I'm going to call it 1/2 x cubed. I'm spinning around. You know, I am doing a horizontal axis, which makes me think I'm working in x's. I'm going around a horizontal axis. My disk is going to kind of go like, shaped like this. And I need the radius of my disk, which is this distance. I need the radius of my disk, r of x, which is that distance. I just drew a picture of that radius. I tried to use this color blue. That didn't work too well. I need that. That's the radius. You draw your radius from the axis of revolution to your outer edge of your shape. Oh, by the way, is there a hole in it? No, the region is flush up against the axis of revolution. There's no hole. So I don't have to subtract out any inner volume. But I do have to get this radius, which is this distance, which is not y. That is not y. Used from the x-axis up, we call that distance y, which is the function. This is not y. That is y. That is 4. So what's remaining there? 4 minus y. Now, I don't want it in terms of y, so it's 4 minus y, and the name of y is the function 1/2 x cubed. But that distance, I'm not subtracting out an inner volume. I'm not subtracting out an inner volume. I am subtracting, I've got an upper and a lower graph for my radius. My radius is that top y minus that y. And then I'm spinning it around y equals 4. There's no hole in it, but my radius itself has involved subtraction. So that's a little different example. That's good. I'm doing several good examples for you. I'm ready though. That's the hard part, is figuring that out. Let's see, what else do I need to figure out? I think I need this x value. I need this. These disks are going to move from 0 to whatever that x value is. When y is 4, maybe I can figure out this x. When y is 4, multiplied by 2, that's 8 equal, oh, okay. X cubed is 8, that means x is 2. Okay. When x is 2, y is 4, that's what I need. So I'm going to set up an integral. Pi, this will be the volume of this shape. There's a pi out front. The radius is now this binomial squared, dx. Again, it's just one radius squared, but it involves subtraction. Because I'm going around the line y equals 4. The bounds are 0 to 2. These disks are x values from 0 to 2 to go throughout this region. Cool. All All right, this video is getting a little long. I may let you do that one. That's pretty good. Listen, you FOIL it. You can do the algebra and FOIL it out, and then integrate. It's not the worst thing in the world. Evaluate from 0 to 2. Unless you wanted to race me, I could race you. What do you think? 1 minute? Think I can do it in 1 minute? Your mark, get set, go. I guess I'll do it for you. And FOIL it. 16 minus the product of those two doubled. That's going to be 2x cubed. When I double it, it's going to be 4x cubed plus a 1/4 x to the 6th, I guess. That is me FOILing it out. I have not integrated yet. Now I'll integrate with respect to x. All right, I think I FOILed that out. Here I go. Oh, there's a pi out front. Here I go, integrate 16x. X to the 4th, divide by 4, that's nice. X to the 7th, divide by 7, wow. 128, x to the 7th. Evaluate from 0 to 2, plug it in. That's 32 minus 16 plus 128 times 2 to the 7th. 2 to the 7th is 128. Plug in your 0 and you get a bunch of zeros. So there's the answer. So this didn't take me too long. Let's see, what's 128 28ths? Can I reduce that by 4? That's 32 sevenths. Get a common denominator, 100, wow, 134 sevenths times pi. Did I do that right? Multiplied by 7. No, that's 144. Sorry. 144 sevenths. I should have known that. Times pi. That's the volume. Awesome. That didn't take too long. All right, good luck. That's a lot of good stuff in 7-2. A lot of good advanced problems. Good luck. Do some problems.